Welcome to All in All. Today we are embarking on, a really deep dive into a substance that holds this truly fascinating duality, diamond. For centuries, it's been revered, as a symbol of timeless luxury, wealth, permanence, all that. But if you look closer, you'll find it's also, rapidly becoming one of the most cutting-edge materials for the future.
Absolutely.
It's underpinning advancements you might never even connect with a glittering gem.
That's completely right. We've got a stack of sources here, articles, research papers, some notes exploring diamond from its, violent, pretty mysterious origins deep within our planet,
Right.
all the way to its, frankly, mind-bending potential uses. Things like quantum computers, advanced medical implants, high-performance electronics. It really is a material that spans billions of years and, at the same time, pushes the boundaries of modern science and engineering.
So our mission in this deep dive, then, is to unpack all of this for you. We want to understand diamond's origin story, its fundamental significance, like, why does it really matter beyond the jewelry store?
Yeah, the core reasons.
Exactly. Its broad impact on the world, how its role has, dramatically evolved over history, and its surprising, really vital relevance today, and what it promises for tomorrow.
It's quite a journey.
It is. It'll take us from these fiery volcanic pipes we hear about to pristine lab chambers, revealing a material with just unparalleled physical, thermal, electrical properties.
Precisely. We'll explore how nature actually crafts it under, unimaginable pressure, how we've learned to recreate it, even engineer it in labs, and the myriad ways it's quietly shaping industries, often in places you least expect to find something called diamond.
Okay, let's dig in then. Let's unpack this incredible material story right from the beginning. Where does diamond actually come from? Let's start with the natural formation.
Okay, so naturally, diamonds are born under truly extreme conditions. We're talking deep, deep within the Earth's mantle.
How deep are we talking?
Typically depths ranging from about 93 to 150 miles down. I mean, just think about that for a second. That's way deeper than the deepest ocean trenches tall, multiple times over.
Wow, that feels incredibly remote from, our perspective up here on the surface. And the conditions down there must be just unlike anything we experience.
Oh, completely. The defining factors are immense pressure and high temperatures. At those depths, the pressure is just staggering. We're talking tens of thousands of times the atmospheric pressure at sea level.
Just crushing.
Absolutely. And for some diamonds, the ones we call super deep diamonds, originating maybe 500 to 600 miles down in the lower mantle, the pressure is astronomical, around 240,000 times atmospheric pressure.
Unbelievable.
Combine that with temperatures between, say, 1,000 and 1,400 degrees Celsius.
Right.
Well, it's the perfect crucible for carbon atoms to compress and arrange themselves into that incredibly dense, stable crystal structure we know as diamond.
So you need carbon, you need that insane pressure and high heat. Okay, but how on earth do they get from way down there, locked inside the mantle, all the way up to the surface where we can actually find them? It's not like they just, float up slowly.
No. It's a very specific and pretty dramatic geological event. They're brought up by these deep source volcanic eruptions. Now, these aren't your typical surface volcanoes. They're quite rare, actually, and incredibly powerful, originating much, much deeper.
Right.
They basically force material from the mantle upwards through these narrow conduits in the Earth's crust. We call them kimberlite and lamprite pipes.
Kimberlite pipes, okay.
Yeah, the molten rock, the magma in these pipes acts like a kind of geological elevator.
Okay.
It carries bits of the deep mantle, including any diamonds that happen to be there, very rapidly towards the surface before it cools. And that fast descent, that's crucial.
Why is speed so important?
Because if the diamonds traveled too slowly, they'd actually become unstable at the lower pressures nearer the surface. They could literally turn back into graphite, which is, the much more common form of carbon.
Ah, so they're like geological passengers on this very specific high-speed train from the deep earth. Fascinating. And some of these natural diamonds are just astonishingly old, aren't they?
Absolutely. Many natural diamonds are ancient, on a geological timescale. Some found near the surface have been dated to be up to, get this, 3.5 billion years old.
3.5 billion years. That's almost as old as the Earth itself. Wow. It makes sense why they carry such a weight of history then. What scientific value do these natural diamonds hold? Especially the ones that aren't, perfect enough for jewelry?
Right. This is where the imperfections actually become incredibly valuable to scientists. You see, imperfect natural diamonds often contain tiny inclusions.
Inclusions, like little bits trapped inside.
Exactly. Microscopic bits of other minerals, fluids, even gases that got trapped inside when the diamond was forming, deep underground. These inclusions, they're like miniature time capsules. They preserve actual samples of the extreme pressure, temperature, and chemical conditions of the deep Earth environment.
Uh,
The moment the diamond formed, potentially billions of years ago.
so the diamond lattice basically froze a tiny sample of its birthplace,
Yeah.
like a snapshot.
Precisely. Researchers study these inclusions intensely because they give us really the only direct samples of material from the Earth's deep mantle, sometimes even deeper. It's like getting a tiny geological core sample from places we could never, ever drill into or access otherwise.
Wow.
They give us invaluable clues about, the composition, temperature, the dynamics of our planet's interior. It helps us understand processes like plate tectonics, the Earth's thermal evolution. They really are tiny snapshots of our planet's history preserved in diamond.
That is truly fascinating, that something valued for its purity and perfection in one context, like jewelry, is scientifically priceless because of its impurities and imperfections in another.
It's a great paradox, isn't it?
It really is. Now, as amazing as natural diamonds are, they obviously have limitations for many modern industrial and high-tech needs. They're rare, they're expensive, their properties can vary quite a bit depending on natural impurities. And that's led to the development and really the rise of synthetic production, right?
Precisely. The increasing demand for diamonds with specific controlled properties, particularly for really demanding requirements in industries like semiconductors, advanced manufacturing, it just couldn't be met by natural reserves alone. So this really drove the need to, replicate the process in a lab.
And there are two main methods for synthesizing diamonds today.
Yes, the two primary methods that really dominate are high temperature, high pressure, which we usually just call HPHT,
HPHT.
and microwave plasma chemical vapor deposition, or MPCVD.
Okay, let's start with HPHT. It sounds like you're literally trying to reproduce the conditions of the deep Earth.
That's essentially what it is. HPHT synthesis involves recreating those immense pressure and high temperature conditions found in the Earth's mantle, but, in a controlled laboratory environment. You typically use pressures between, say, 5.5 and 8.0 gigapascals.
Which is, how much pressure is that?
Well, it's equivalent to being maybe 80 miles under the sea. That kind of pressure. And you combine that with temperatures from 1,000 to 1,400 degrees Celsius.
So you're basically squeezing and cooking carbon.
Yes, exactly. Usually starting with a carbon source like graphite. The process often involves a metal catalyst, things like nickel, iron, or cobalt, which helps dissolve the carbon at that high temperature and pressure. Then it allows it to crystallize as diamond around a tiny seed crystal.
A seed crystal, like a template.
Exactly. It gives the diamond structure something to grow onto. And research is ongoing into different growth environments, looking at how the presence of other elements like nitrogen or oxygen, hydrogen, even water or silicates influences the growth rate and the quality. Interestingly, studies have shown that the transformation from graphite is actually favored in water-enriched environments under these conditions.
That maybe mirrors some ideas about how it happens naturally.
It could, yeah. It adds to the picture.
What are the pros and cons of this HPHT method for making diamonds?
Well, HPHT is very well established. It's efficient for producing a large volume of industrial-grade diamonds, often smaller crystals or polycrystalline materials used for abrasives and cutting tools. The technology is mature, it works.
Okay, but the limitation.
The main limitation, especially for advanced electronic or optical applications that need large, high-purity single crystals, is size. HPHT single crystal diamonds are generally limited to sizes smaller than about 10 millimeters, maybe half an inch, in their largest dimension. And that restricts their use as substrates for certain types of devices.
Okay, so HPHT is the direct mimic of nature. Good for industrial grit, but size limited for high-tech single crystals. What about MPCVD then? You mentioned that's becoming more dominant, especially for the high-tech stuff.
Right, MPCVD, or microwave plasma chemical vapor deposition. It's a fundamentally different approach. Instead of bulk compression, it builds the diamond crystal literally atom by atom from a gas phase.
Atom by atom. How does that work?
Okay, so you have a reaction chamber, usually a vacuum chamber. Inside, you place a substrate material, often a small piece of existing diamond, natural or synthetic, or sometimes another suitable crystal. This substrate is heated up, typically to temperatures between 800 and 1,200 degrees Celsius.
Pretty hot.
Oh yeah. Then you introduce a gas mixture into the chamber. It's usually mostly hydrogen, with just a small percentage of a carbon-containing gas, like methane. Then microwave energy is beamed into the chamber, and this generates a plasma right above the substrate.
The plasma, so like a superheated ionized gas, like lightning in a box.
Exactly, that's a good way to think of it. The microwave energy breaks down the gas molecules in this plasma. Now, the hydrogen atoms are absolutely crucial here. They do a couple of things. They help etch away any non-diamond carbon, like graphite, that might try to form.
Keeps it clean.
And they terminate the diamond surface in a way that allows new carbon atoms to attach properly. Then, the reactive carbon species, which come from the methane breaking down, travel through the plasma and deposit onto that heated substrate, building up the diamond crystal layer by layer.
So it's kind of like highly controlled atomic scale spray painting of diamond onto a surface, almost.
That's actually a pretty good analogy. It is vapor deposition. You're building up the film from the gas phase. Now, several factors are really critical for getting good growth. The exact gas mixture composition, the pressure in the chamber that affects the plasma shape, its stability, the types of active species created, and especially the substrate temperature.
And temperature is key for quality, I'm guessing.
Oh, absolutely critical. You need that sweet spot. Temperatures between 800 and 1200 degrees C are typical for good quality, reasonably fast growth. If you go below about 750 degrees C, the growth rate just plummets and the quality suffers. You get more defects. Go much above 1200 degrees C, and you risk actually etching away the diamond or even converting the newly grown diamond back into graphite. Not good.
Right. What are the main challenges researchers face with MPCVD, trying to make these perfect diamond layers?
One significant challenge, especially when you're trying to grow large area single crystal diamonds, is achieving perfectly homogeneous growth, uniform growth across the whole substrate.
Meaning it grows unevenly.
Yeah, you often see faster growth rates happening at the edges of the substrate compared to the center, and this can lead to lower quality or even polycrystalline growth, like lots of little crystals, instead of one big perfect one forming at the edges. This is linked to non-uniformity in the plasma itself, specifically gradients in the electron number density.
So the plasma isn't perfectly even, and that messes up how the diamond grows.
Exactly. The distribution of those reactive carbon bits and the crucial hydrogen atoms is tied directly to the plasma characteristics. Researchers tackle this using various tricks, like optimizing the chamber design, how the microwaves are delivered, and using specifically designed substrate holders. These holders might have particular shapes or cavity depths.
Oh, all right.
And they help modify the plasma shape and balance out that electron number density distribution right near the substrate. The goal is to promote more uniform growth over larger areas. And this ability to grow larger, higher quality single crystals is really a key reason MPCVD has become so dominant for these high-tech applications.
Okay, so we have natural diamonds formed over billions of years deep underground, and then we have lab-grown diamonds synthesized relatively quickly by either HPHT or MPCVD. For someone just looking at them, say, in a jewelry store, what's the real difference? Are they truly the same material?
This is such a crucial point, and yeah, where a lot of the discussion happens, especially in the consumer market, chemically and physically. A lab-grown diamond that is pure carbon arranged in that specific diamond lattice structure is identical to a natural diamond that's pure carbon arranged in the same structure.
Identical.
Identical. Both are just carbon atoms in that specific crystal lattice. They have the exact same hardness, the same thermal conductivity, the same optical properties like brilliance and fire. From a material science perspective, they are diamond.
But the market treats them very, very differently, especially for jewelry.
Oh, absolutely. The primary difference really lies in their origin, their history, and, well, the associated emotional, cultural, and social value that we've assigned to them over centuries. Natural diamonds carry that mystique, right? Formed over billions of years inside the earth.
That deep time connection.
Exactly. They're deeply associated with tradition, heritage, wealth, exclusivity, romantic symbolism, and that's been heavily reinforced by decades of marketing and the prestige of high-end brands, like Tiffany or Cartier. Lab-grown diamonds, while chemically the same, just don't have that deep geological history or that traditional cultural narrative in the jewelry context.
Which naturally leads to a massive difference in price.
A very significant difference, yes. Because the supply can be controlled, the production method is less resource-intensive, less constrained by rarity. Lab-grown diamonds are substantially cheaper. You can typically find lab-grown diamonds that are, say, 70% to 90% less expensive than a natural diamond of comparable size, cut, color, and clarity.
Huge difference.
Yeah.
Are there any subtle differences in their physical makeup, maybe impurities or something, that can help distinguish them, even if the core carbon structure is identical?
Yes, often there are. The types and patterns of impurities, or those inclusions we talked about earlier, can give clues to their origin. Natural diamonds almost always contain trace amounts of nitrogen because nitrogen is present in the Earth's mantle where they form.
Ah, okay.
This nitrogen can be dispersed through the crystal or clumped together in different ways, and sometimes it causes a slight yellow or brown tint. Now, truly colorless, nitrogen-free natural diamonds called type Tia, they do exist, but they are incredibly rare and command extremely high prices. Lab-grown diamonds, on the other hand, particularly those made by CBD, can often be grown specifically to exclude nitrogen. This results in very high purity and often colorless crystals, type Tia or type IB if they're intentionally doped with boron for electronic purposes. This high purity is actually a requirement for many of the advanced tech applications.
So the purity can be a clue. What about inclusions?
Yeah, inclusions differ too. HPHT lab-grown diamonds, if the process isn't perfectly controlled, might trap trace amounts of the metallic catalysts used like nickel or iron. Sometimes these can be detected with a microscope, or occasionally even by checking if the diamond is slightly magnetic.
Magnetic diamond. Weird.
It can happen. CVD diamonds might show different types of inclusions altogether, like tiny graphite particles that look like little black pinpricks, or maybe comet shapes, or flat, cloud-like features under magnification. These look different from the tiny mineral crystals you often find trapped inside natural diamonds. Gemologists use these subtle differences, often combined with advanced techniques like spectroscopy, to determine the origin, natural or lab-grown.
So while the fundamental carbon structure is the same diamond, the trace elements and the tiny things trapped inside often tell the story of how and where it was made. Okay, let's move beyond their origin story. Let's talk about why diamond truly matters. What are its fundamental properties that make it so unique, so valuable across such a huge range of applications?
Right. Diamond possesses this amazing combination of extreme properties that very few, if any, other materials can rival all at once. The most famous one, of course, is its hardness.
The hardest thing there is.
It's the hardest known natural substance on the planet, yes. Its name actually comes from the ancient Greek word adamas, meaning unconquerable or invincible.
So it's incredibly resistant to scratching, abrasion, wear and tear.
Exactly. This extreme wear resistance makes it invaluable for cutting, grinding, drilling, polishing, anything that involves intense friction or abrasion. However, it's important to remember something. Hardness is resistance to scratching and indentation. Despite its famous hardness, diamond is also relatively brittle compared to, say, metals.
Brittle? How so?
It means a sharp impact or force applied along a specific crystal plane can actually cause it to cleave or shatter. This is actually how traditional diamond cutters work. They exploit these cleavage planes using controlled impacts with chisels. They don't just try to saw through it with brute force.
Huh. That brittleness is a surprising contrast to its legendary hardness. What other properties make it stand out so much?
Okay, another huge one, thermal conductivity. Diamond is the best-known thermal conductor, period. It dissipates heat incredibly efficiently, significantly better than any metal, and something like 5 times better than silicon, which is, the foundation of most modern electronics.
So it just whisks heat away super effectively.
Precisely. And this is absolutely crucial for high-performance electronic devices. As chips get faster and smaller, they generate immense heat. If you don't manage that heat, the device slows down, becomes inefficient, and eventually fails. Diamond acts like an incredibly efficient heat sink, just pulling that damaging heat away faster than anything else. Then there are its electrical properties. Pure, intrinsic diamond with no impurities is an excellent electrical insulator. It has a very wide band gap, about 5.47 electron volts.
Band gap. Remind me what that means again.
Think of the band gap like an energy barrier that electrons have to jump over to move around and conduct electricity. A wide band gap, like diamonds, means it's very hard for electrons to make that jump. So it doesn't conduct electricity easily, making it a great insulator that can withstand very high voltages without breaking down and letting current flow. This is critical for power applications.
But you mentioned earlier it can also be a semiconductor. That sounds like the opposite.
Yes, that's the other side of the coin. While it's intrinsically an insulator, its conductivity can be precisely controlled by adding tiny amounts of specific impurities. That process is called doping.
Right, doping.
If you introduce elements like boron, you create what's called p-type conductivity, where positive holes carry the charge. If you introduce elements like nitrogen or phosphorus or sulfur, you can create n-type conductivity, where electrons carry the charge. This ability to switch it from being a superb insulator to a controllable semiconductor is what makes it potentially revolutionary for electronics, especially high-power devices.
Okay, and what about its interaction with, say, chemicals or even living things?
Diamond is also remarkably chemically inert. It doesn't react easily with most chemicals or acids. That gives it great stability in harsh environments. And crucially for medical applications, it's highly biocompatible,
Biocompatible meaning?
meaning it doesn't provoke a toxic response or significant inflammation when it's in contact with living tissue. It can be safely implanted in the body for long periods without causing problems.
Okay, those are some truly extreme properties. Now, beyond the purely scientific side, diamond has obviously had a profound societal and economic impact on the world.
It certainly has, and it's a complex picture with both significant positive contributions and historically some very serious challenges. Financially, diamond mining and trade represent a really significant portion of the GDP for several diamond-producing nations, particularly in Africa.
Right.
And the whole global commodity chain, from the rough stone being mined, then sorted, cut, polished, then manufactured into jewelry or industrial tools, and finally sold at retail, that whole chain generates considerable wealth and employment across the globe, from African mining communities to cutting centers in places like India and retail markets everywhere.
But that economic impact has also been tragically tied to conflict and suffering, hasn't it? The whole issue of blood diamonds.
Tragically, yes. Historically, diamonds mined in war zones were sold, often illicitly, to finance brutal civil wars and armed conflicts, particularly in parts of West Africa in the 90s. These became known as blood diamonds or conflict diamonds, and the trade fueled violence, instability, and caused immense human suffering.
That must have been a huge challenge to the industry's reputation and just morally horrific. How has the world tried to address that problem?
The main international response has been the Kimberley Process Certification Scheme, which was established back in 2003. It's a joint effort involving governments, the diamond industry itself, and civil society organizations. The goal is to prevent conflict diamonds from entering the legitimate rough diamond market.
How does it work?
Basically, participating countries have to implement strict internal controls and a certification system for all exports and imports of rough diamonds. Shipments have to be in tamper-resistant containers and accompanied by a government-validated Kimberley Process certificate stating they are conflict-free.
And has it been effective? Has it worked?
Well, since its implementation, the Kimberley Process claims to have certified approximately 99% of the world's legitimate diamond supply as conflict-free. It has definitely significantly reduced the global trade in conflict diamonds compared to the situation in the late 1990s. Now, it's not without its critics. There are ongoing debates about its scope, enforcement, and whether it addresses broader human rights issues beyond conflict financing, but it has made a substantial difference.
Beyond conflict diamonds, there's also this increasing focus now on broader sustainability and ethical practices in pretty much all industries, right? How's that affecting diamonds?
Absolutely. Growing consumer awareness and regulatory pressure for ethically sourced and environmentally responsible products is definitely pushing the entire diamond industry, both natural and lab-grown, towards greater transparency and sustainability.
What kind of efforts does that involve?
It includes things like improving mining practices to reduce environmental impact, investing back into mining communities through corporate social responsibility or CSR programs, using carbon offsetting schemes, transitioning to renewable energy sources in mining and synthesis operations. And of course, the rise of lab-grown diamonds with their different production footprint offers consumers an alternative if specific environmental or ethical concerns are their priority.
Now, looking back a bit at the history of diamonds' attempted adoption in technology, you mentioned earlier there were some really high hopes, maybe some hype early on that didn't quite pan out as expected.
That's a really interesting pattern you see with revolutionary materials sometimes. Diamond's extreme properties led to tremendous early optimism, yes. People dreamed it would become the ultimate semiconductor or completely transform various high-tech fields almost overnight.
Can you give some examples? Where did diamonds seem like a perfect fit, but maybe adoption was slower or didn't happen as planned?
Okay, a classic example is in surface acoustic wave filters, or SAW filters. These were important components in early mobile phones and other communication devices. Now, diamond has this astonishingly high acoustic velocity. Sound travels through it incredibly fast, about 19 kilometers per second.
Wow, that's fast.
It's incredibly fast, roughly 40 times faster than sound in air. This property was theoretically ideal for creating really compact, high-frequency, high-performance SAW filters.
So, on paper, it looked like a game changer.
Huge potential, yeah. The hope was for vast improvements in filter performance, smaller devices, but the technical reality turned out to be really complex. Actually, interfacing the diamond with the other materials needed to make the device work, particularly the piezoelectric materials you need to convert electrical signals into those acoustic waves and then back again, that proved much more difficult and time-consuming than people initially anticipated. Optimizing the fabrication processes for these diamond-based devices just took far longer than expected.
And while the researchers were wrestling with those integration challenges, what happened?
Well, competing materials and technologies that were maybe easier to work with started to emerge and improve rapidly. Even if these alternative materials were, on paper, inferior to what diamond could potentially achieve, they reached a point where they were good enough. And crucially, they were more reliable to manufacture and much easier and cheaper to produce at scale using existing semiconductor fabrication techniques. So manufacturers were faced with this choice. Pursue the difficult, long, expensive development path for diamond SAW filters, or go with a viable, easier alternative that was available now. Many chose the easier path.
So the good enough and readily manufacturable option won out over the potentially superior but much harder to implement diamond.
Exactly. It became a recurring theme for a while. Remarkable properties generating huge hopes, followed by unexpected technical hurdles in fabrication or integration, and then competition from alternative technologies that were simply easier to commercialize.
Any other examples of that?
Yeah, field emission displays, FEDs. There was a lot of excitement about these in the late 1990s. The idea was to use arrays of tiny, sharp emitters, often made from diamond films or carbon nanotubes, to generate electrons that would light up pixels on a screen.
Flat screens using diamond.
That was the dream. And there were some promising prototypes. But ultimately, FEDs lost the market race to LCDs, then LEDs, and later OLED screen technologies. It largely came down to factors like manufacturing cost, large area uniformity, reliability, and the fact that these other good enough flat screen technologies became widely available to consumers sooner and cheaper. R&D and diamond field emission displays pretty much wound down in the early 2000s.
It seems like a common thread then. Diamond's incredible potential was recognized early, but the sheer technical difficulty of using it, effectively integrating it into functional devices, developing reliable manufacturing processes at scale, that was a major bottleneck that stalled adoption in several promising areas in the past.
That's a very fair summary. The fundamental properties were always known to be outstanding, but the material science and the engineering challenges involved in actually working with diamond, especially making large, perfect pieces and integrating them smoothly with other materials, proved much more complex than for many other conventional semiconductors or structural materials. But, this historical context actually makes the current resurgence in diamond technology even more exciting.
How so?
Because it shows that we're finally starting to overcome many of those past limitations, thanks to advances in synthesis and processing techniques.
Okay, that's a good transition. Let's trace the evolution of how we've actually used diamond over time, starting from ancient history right up to the present day.
Right. Well, historically, for millennia, diamond was valued almost exclusively as a gemstone. Its primary appeal was purely aesthetic, its extraordinary brilliance, its ability to refract and disperse light, creating that fire and sparkle we associate with it.
And cutting techniques really enhanced that, right?
Yeah, massively. The visual appeal was dramatically enhanced as cutting techniques improved. There were key developments in the 1870s with the invention of machines that could precisely cut facets, and then it was further refined by Marcel Twelkowski in 1919. He was the one who mathematically calculated the optimal proportions for the round, brilliant cut to maximize light return and sparkle.
So for most of history, it was primarily a symbol of beauty, status, wealth, used for adornment.
Yes, largely for jewelry, with maybe some very simple industrial uses leveraging its hardness, like using rough, uncut diamonds to polish other gems or maybe engrave some hard materials. The major turning point for diamond as a truly industrial material came much later, really in the mid-1950s.
And that connects back to the invention of HPHC synthesis, doesn't it?
Precisely. The ability to reliably synthesize diamond using that HPHT method and to do it on a larger scale enabled the creation of what became known as industrial diamonds.
What were these like?
Typically, they were smaller crystals, often with more defects or maybe some discoloration compared to gem-quality diamonds, that made them unsuitable, or at least undesirable, for jewelry. But they were perfectly functional, and, importantly, cost-effective for applications that primarily needed extreme hardness and wear resistance.
So this wasn't about sparkle anymore. It was purely about utility, about toughness.
Exactly. Their value was in their function. They were rapidly adopted for really demanding mechanical applications. They became crucial for cutting and machining hard metals and ceramics used in manufacturing, for precision polishing and grinding of optical components like lenses.
What kinds of tools used them?
Oh, lots. Industrial diamonds were used as loose abrasives, like tiny diamond particles mixed into a paste for polishing, or they were embedded directly into tools. Things like massive saw blades for cutting concrete and rock in construction, drill bits for mining and deep-sea oil drilling, specialized dies for drawing metal into fine wires, and grinding wheels for shaping hard materials. You could actually find diamond-coated tools like blades for cutting tile or grinding tools showing up in local hardware stores starting around the 1960s. Diamond really transitioned from being just a precious gem to being a vital workhorse material in heavy industry.
So the mid-20th century saw diamond become this industrial staple, mainly for its hardness. What's driven the evolution in more recent decades? What's led to its potential in all those high-tech areas we hinted at earlier?
Right, the past few decades, and I'd say particularly gaining significant momentum from around 2010 onwards, have really seen a renaissance in diamond synthesis technology, especially with the increasing dominance and sophistication of that MPCVD method we discussed. This has enabled the growth of much larger single crystal diamonds.
Bigger pieces.
Bigger pieces, yes, and with unprecedented levels of purity and control over defects.
So the quality and size of synthetic diamonds just improved dramatically.
Precisely. This availability of higher quality material, especially the ultra-high purity single crystal CVD diamond, often with very low nitrogen content, became accessible for scientific research and for serious technological development. This access to material that was previously either extremely rare and expensive or simply impossible to obtain in the needed quality really fueled a massive expansion in potential application areas. The focus started to shift from primarily leveraging its hardness and thermal conductivity to actively exploring and exploiting its unique semiconductor properties, its optical properties, and even the properties of specific defects within the diamond for really advanced applications.
Okay, let's talk about that modern relevance then. Where are we actually seeing diamond used, or where is it poised to be used in practical applications today and in the near future?
The range is truly vast now, extending far, far beyond its historical uses. Mechanically, of course, diamond is still absolutely critical in cutting, milling, grinding, and drilling tools. That hasn't gone away.
Still the king of hardness.
Pretty much. It's used in those massive saw blades for cutting concrete and asphalt on roads, in drill bits for mining and oil exploration that have to chew through the hardest rock formations, in precision grinders for manufacturing engine components or turbine blades, and in those wire drawing dies to create very fine metal wires for electronics. HPHT diamond, often sintered together with a metal binder like cobalt to form these tough polycrystalline diamond or PCD blocks, still dominates many of these heavy-duty applications. But high-quality CVD diamond is increasingly finding its place, especially where precision or specific properties are needed.
What specifically makes it so effective in these tools? Is it just the hardness?
It's more than just the hardness, though that's obviously key. The extreme wear resistance means the tools last incredibly long. That reduces downtime for tool changes, cuts replacement costs. But equally important, maybe even more so in some cases, is its incredibly high thermal conductivity.
Right, pulling the heat away.
Exactly. Cutting and grinding generate enormous heat right at the cutting edge. Diamond's ability to rapidly conduct that heat away keeps the tool cooler. This prevents the tool material from softening or degrading, which increases the tool's lifetime dramatically, often by a factor of 10 or even more, compared to tools made from other hard materials like tungsten carbide. It also allows for higher cutting speeds and feed rates, which boosts productivity. And its low friction coefficient also helps it reduces the heat generated in the first place and improves the efficiency of material removal. And beyond heavy industry, diamond is also crucial in high-precision scientific instrumentation now. For example, you find diamond or diamond-coated tips used in atomic force microscopy AFM.
AFM. It's for imaging things really small, right?
Exactly, imaging surfaces at the nanoscale. In AFM, you scan a very sharp tip over a surface to map its topography. Using a diamond tip, especially one made from boron-doped diamond, BDD, which is conductive, significantly improves resolution and, crucially, prevents the tip itself from wearing down or getting damaged when you're imaging very hard surfaces, especially in contact mode imaging. You can even get clever and decorate these diamond tips with specific nanoparticles to give them catalytic properties, so you can combine mechanical imaging with localized chemical analysis.
And diamond is also essential in high-pressure physics research you mentioned.
Yes, absolutely central, in devices called diamond anvil cells, or DACE. These use two extremely hard gem-quality diamond anvils, which are precision cut with very small, flat tips called cullets. You place a tiny sample of material, maybe just a few microns, across between these tips, often with a metal gasket around it. Then you apply immense force, squeezing the diamonds together.
How much pressure can they generate?
Astonishing amounts. Researchers can generate pressures equivalent to those found deep inside planets. We're talking millions of atmospheres. This allows them to study how materials behave, what phases they transform into under these extreme conditions. It provides vital insights into planetary science, geophysics, and fundamental material properties that you just couldn't get any other way.
Okay, switching gears now to electronics. This seems to be where diamond's unique electrical and thermal properties really come into play.
Absolutely. Diamond is gaining significant attention, a lot of research funding for high-power electronics. As we touched on, its unique combination of the highest thermal conductivity of any known material, plus an extremely high electrical breakdown field.
Meaning it can handle high voltage.
Exactly. It can withstand very high voltages before it starts conducting current uncontrollably and fails. This combination makes it theoretically ideal for managing heat and handling very high voltages and currents simultaneously, much better than silicon or even current wide bandgap materials like silicon carbide or gallium nitride.
Where would you actually need these extreme capabilities?
Think about applications involving high-efficiency power conversion and management. Things like power converters and inverters used in electric vehicles, charging infrastructure, integrating renewable energy sources like solar and wind onto the grid, industrial motor drives, and perhaps most significantly, massive data centers.
Data centers, why there?
Data centers consume absolutely huge amounts of electrical energy, and a significant portion of that energy is actually wasted as heat during power conversion and by the servers themselves. Plus, they require enormous cooling systems. Diamond-based power devices could potentially operate much more efficiently, reducing energy loss, and because they can handle higher temperatures, they might simplify cooling requirements. This could lead to significant energy savings and reduced operating costs. Basically, any application that needs to handle a lot of power very efficiently, especially if it needs to operate reliably at high temperatures, diamond looks very, very attractive.
You mentioned the wide bandgap makes it a good insulator, but also that doping turns it into a semiconductor.
Yeah.
How does that wide bandgap specifically help in high-power devices?
So wide bandgap semiconductors are crucial for building power electronic devices like transistors and diodes that can switch on and off very quickly, handle high voltages without breaking down, and lose minimal energy as heat during operation. There's a key metric engineers use called the Baliga figure of merit, or BFOM.
BFOM, okay.
Yeah, this metric basically relates a material's ability to withstand high voltage, its breakdown voltage, to how much electrical resistance it presents when current is flowing through it, its specific on resistance. A higher BFOM means you can theoretically build devices that are smaller, faster, and lose much less energy as heat when they're conducting current. This translates directly to higher efficiency. Diamond has some of the highest theoretical BFOM values compared to all known semiconductors, including the currently commercialized wide bandgap materials like silicon carbide, 6-SCEIT, and gallium nitride, DGN.
So on paper, diamond looks like the ultimate power semiconductor material. The champion.
Theoretically, yes, it has the potential. But, and this is a big but, there are still significant engineering challenges to overcome before it becomes widespread. One of the main ones is achieving effective and reliable doping.
Making it conduct electricity predictably.
Exactly. Reliably introducing controlled amounts of those impurity atoms like boron for p-type or phosphor-sulfur for n-type into the diamond lattice to achieve consistent conductivity levels and maintain high carrier mobility, how easily the charges move, is still quite difficult compared to silicon or even SECA and GaN. Boron doping to make p-type diamond is relatively well understood now, but things like its activation energy, the energy needed to actually make the boron atoms contribute charge carriers, can vary with concentration, and achieving high mobility at the high doping levels needed for low resistance remains a challenge. Interestingly, if you dope diamond very heavily with boron, it can even become superconducting at very low temperatures.
Superconducting diamond.
Yeah. But N-type doping, making it conduct with electrons, that's proven even harder to achieve reliably with high performance. Researchers are still working hard on finding the best N-type dopants and activation methods. But despite these difficulties, researchers are making significant progress in fabricating actual diamond electronic components. They're developing things like Schottky diodes. These are relatively simple semiconductor devices formed by placing a suitable metal contact directly onto the diamond's surface.
What metals work?
Different metals are being tested, things like tungsten, aluminum, chromium, nickel, zirconium. Zirconium seems to show particularly stable electrical contact properties with diamond. Often they use layered metal stacks, maybe like zirconium, platinum, gold as the electrode. And you can also tune the electrical behavior of this metal-diamond contact by modifying the diamond surface itself chemically, for example, by terminating the surface atoms with oxygen or fluorine atoms before depositing the metal.
And I've heard about some specific diode structures like PDSBDs. What are those?
Yes. Pseudovertical Schottky barrier diodes, or PVSBDs. These are a particularly promising structure for diamond-powered devices. They are fabricated on insulating diamond substrates, and the clever design allows current to flow primarily downwards, vertically, through the diamond layer. This geometry can achieve very high current density over a smaller device area compared to lateral designs. Researchers have demonstrated PVSBDs made on diamonds showing really impressive results. Very high breakdown fields, incredibly low on resistance values, meaning less energy loss, excellent rectification ratios, meaning they block current very effectively in the reverse direction, and good stability at high temperatures. They're even exploring using different crystal orientations of the diamond substrate, like the 113 orientation, to try and optimize performance further. Another really exciting area, related but different, is the 2D whole gas, or 2DHG.
2D whole gas. Sounds exotic.
It is pretty cool. It's this phenomenon where a very thin, highly conductive layer forms right on the surface of the diamond after it's been treated with hydrogen plasma. You see, a hydrogen-terminated diamond surface has this unique property called negative electron affinity, or NEA.
Negative electron affinity.
It essentially means it's energetically favorable for electrons from the surrounding environment, particularly for molecules like water absorbed from the air, to actually transfer onto the diamond's surface atoms. When these electrons transfer away from those surface molecules to the diamond, they leave behind holes, which are like positive charge carriers right at the diamond surface. These holes are mobile and form a highly conductive two-dimensional layer, just nanometers thick.
So just treating the diamond surface with hydrogen and exposing it to air can make the very top layer conductive without doping the bulk.
Exactly. It's a fascinating surface effect. And this 2DHG layer can be used as the channel to build advanced transistor structures like field effect transistors, FETs, or high electron mobility transistors, ATMTs, right on the diamond surface. These devices could be particularly suitable for applications needing extreme robustness resistance to radiation damage, operation at very high temperatures, handling high power levels, basically, environments where conventional silicon devices would quickly fail.
Okay, so summing up the electronics part. While silicon carbide and gallium nitride are already in commercial products, powering things like electric cars and efficient chargers, diamond electronic devices are still mostly in the research and development stage.
That's the current picture, yes.
But they're showing performance metrics in the lab that suggest they could significantly outperform existing materials, especially in the most demanding, high power, high temperature, or high radiation niches.
That's exactly right. The challenges in growing large area, perfectly uniform diamond wafers, controlling the doping precisely, and integrating these devices into reliable manufacturing processes mean diamond isn't mass-produced for electronics like SECSIC or GaN yet. But the fundamental theoretical potential, backed up by these increasingly impressive research results on devices like PVSBDs and 2DHG EFETs, makes it a material with huge long-term promise for really breaking through current barriers in power efficiency and handling capabilities.
Okay, let's shift focus slightly. Diamond also has unique optical properties, right? It's not just hard and good with heat and electricity.
Yes, absolutely. Especially high-purity CVD diamond. When it's grown with very low nitrogen content, diamond is remarkably transparent across a massive range of the electromagnetic spectrum. spectrum.
A wider range.
We're talking from the deep ultraviolet, right through the entire visible light spectrum that we see, and then well into the infrared and even microwave frequencies. This incredibly broad transparency window, combined with its robustness, makes it really useful for applications where you need a window or an optical element that can survive harsh conditions or handle high power without degrading or absorbing the light.
Like windows for lasers or X-ray machines.
Precisely. Thin diamond membranes are used as durable windows in things like high-power industrial lasers, X-ray machines used for medical imaging or materials analysis, and in vacuum chambers where you need to get light or other radiation in or out without the window breaking or reacting. High-purity CVD diamond infrared optics are even becoming critical components in cutting-edge manufacturing processes like extreme ultraviolet lithography, EUV lithography.
EUV, that's for making computer chips, isn't it?
Exactly. EUV lithography uses extremely short wavelength ultraviolet light to pattern the features on the most advanced semiconductor chips. The optics involved have to be incredibly precise and durable, and diamond's properties make it suitable for certain components in those complex systems. Diamond can also be used for things like anti-reflective coatings on other optical materials, or even as the active crystal material itself in specific types of lasers, like Raman lasers.
Raman lasers. What does diamond do in that kind of laser?
Okay, so in some Raman lasers, you use a crystal to shift the wavelength or color of an incoming pump laser beam to a different wavelength through a process called Raman scattering. For example, you might want to convert common green laser light into yellow light, which has specific applications in areas like medical treatments, spectroscopy, or guiding stars for astronomy. Diamond turns out to be an excellent crystal material for this.
Why diamond specifically?
It has the necessary optical properties for efficient Raman scattering, but crucially, its incredibly high thermal conductivity is a massive advantage here. The intense pump laser beam deposits a lot of heat into the Raman crystal. If that heat isn't removed very efficiently, it causes the crystal to heat up, potentially distorting the laser beam quality or even damaging the crystal, limiting the output power. Diamond's ability to rapidly pull that waste heat away allows diamond Raman lasers to operate at much higher powers and with better beam quality compared to lasers using more conventional Raman crystals like tungstates or vanidates.
Okay, now here's where it gets really futuristic and maybe the most exciting potential application. Quantum technology. Diamond is emerging as a really significant material in the global quest for quantum computers and other quantum devices.
This is arguably one of the most talked about potential applications for diamond right now, yes, and for good reason. One of the major hurdles, maybe the major hurdle, for building powerful, practical quantum computers is that many current types of qubits, the basic units of quantum information, are incredibly fragile.
Qubits, right.
They're very sensitive to noise from their environment, and they usually require extreme supercooling, often down to temperatures near absolute zero, like 10 or 20 Kelvin. That's colder than deep space. This requires expensive, bulky, complex cryogenic refrigeration systems.
And diamond offers a potential path around that costly deep freeze.
That's the big hope and the focus of intense research worldwide. It turns out that certain specific defects within the diamond lattice can function as surprisingly robust qubits that can operate and be manipulated at room temperature.
Room temperature quantum computing.
That's the goal. Imagine the implications quantum computing power that doesn't require those massive, power-hungry refrigeration units. It could potentially enable much smaller, cheaper, and more integrated quantum devices. We're talking possibilities like embedding quantum sensors into a smartphone, or having quantum coprocessors integrated into a standard personal computer, or even a smartwatch someday. It really lowers the barrier to entry.
What kind of defects are we talking about? These aren't just random flaws, are they?
No, they're very specific point defects. The most famous and well-studied one is the nitrogen vacancy center, usually abbreviated as the NV center.
Nitrogen vacancy, NV center.
Okay. This is a specific defect in the diamond crystal structure where one carbon atom is missing, that's the vacancy, and right next to that empty spot, a neighboring carbon atom has been replaced by a nitrogen atom, so nitrogen next to a vacancy.
So it's like a very specific engineered imperfection that creates a useful quantum property.
Exactly. That's a great way to put it. This NV center behaves in a very special quantum mechanical way. You can almost think of it like an artificial atom or a pseudo-atom trapped inside the very stable, insulating diamond crystal. It has distinct electronic energy levels and, importantly, an electron spin associated with it. These quantum properties are sensitive to their local environment, but they're also protected from noise to some extent by the surrounding rigid diamond lattice. A key discovery back in 1997 showed that a single NV defect acts as a stable source of single photons. If you shine green laser light, around 532 nanometers, onto it, the NV center absorbs the light and then re-emits single photons of red fluorescence, around 637 nanometers, one precise photon at a time, on demand. This discovery really opened the floodgates for using diamond in quantum information science.
So it spits out single photons. How does that relate to using it as a qubit for computation?
The qubit is actually stored in the electron spin associated with the NV center. This spin can exist in different quantum states, conventionally labeled spin up, spin down, which can represent the 0 and 1 of a classical bit. But being quantum, it can also exist in a superposition of both states simultaneously. Researchers have demonstrated really impressive control over these NV spin states using precisely timed microwave pulses and laser light.
What kind of quantum feats have they achieved with these NV centers?
Some significant milestones. They've managed to generate and detect quantum entanglement, that famous spooky action at a distance Einstein talked about, between the spins of two separate NV centers, even when those diamonds were physically separated by meters. And in 2015, there was a landmark experiment using entangled NV centers in different labs that demonstrated a loophole-free violation of Bell's inequality. This is a fundamental test of quantum mechanics versus classical physics, and the result provided perhaps the strongest evidence ever that the quantum world truly is non-local and weird.
Wow. Using a defect in a diamond to probe the fundamental nature of reality. That's mind-blowing. Can they also be used for practical sensing, not just fundamental physics? Like you mentioned magnetometry.
Yes, absolutely. NV centers are extremely sensitive to their local environment, particularly to magnetic fields. The energy levels of their spin states shift subtly in the presence of a magnetic field. By shining laser light on the NV center to read out its spin state, based on how brightly it fluoresces, while simultaneously applying microwave fields, you can use a technique called optically detected magnetic resonance, or ODMR, to precisely measure these tiny shifts in the spin energy levels.
And that tells you the magnetic field strength.
Exactly. It allows the NV center to function as a tiny, atomic-scale, highly sensitive magnetic field sensor. It's capable of detecting very weak magnetic fields, potentially down to the level of single molecules or even single nuclear spins, all at room temperature. This has potential applications ranging from fundamental science research to developing new kinds of sensitive medical imaging like magnetoencephalography, measuring brain activity, or even navigation systems that don't rely on GPS.
Okay, let's shift gears again maybe to something that sounds even more counterintuitive at first. How can something known for being the hardest material on Earth be used inside the squishy, delicate human body?
It might sound surprising, yeah, but diamond is actually exceptionally well suited for many biomedical applications. And this comes down precisely to some of those other properties we discussed. Its extreme chemical inertness and its excellent biocompatibility.
Remind us what biocompatibility means in this context.
It means that when diamond is implanted or placed in contact with living tissue, it doesn't trigger a significant adverse immune response. It doesn't cause much inflammation or scarring, and importantly, it isn't toxic or degraded by biological fluids over time. Yeah. This means diamond components can potentially function reliably inside the body for many, many years, maybe even decades, without causing problems or needing replacement.
So it's safe and stable inside our tissues, like an inert passenger.
Exactly. It doesn't react chemically with the complex environment inside the body. This makes it an ideal material for coatings or even structural components in various types of bioimplants. For example, it can be used to encapsulate and hermetically seal sensitive electronic components, like the silicon circuitry used in pacemakers or neural implants, protecting them from the body's corrosive fluids, and also protecting the body from any potentially toxic materials inside the device.
What kinds of bioimplants are we talking about here? Where's diamond being used or explored?
It's becoming a material of choice, or at least a strong candidate, for really advanced neuroprosthetics. This includes things like neural implants designed for sensing electrical activity in the brain or stimulating specific nerves.
Like for treating Parkinson's or epilepsy?
Potentially, yes.
Oh.
Or restoring some function after spinal cord injury. Also, components for future bionic organs and, significantly, interfaces for brain-computer interactions, or BCIs.
Brain-computer interfaces.
Yeah.
That genuinely does sound like science fiction is starting to become reality.
It really is on the cutting edge of medical research. Diamond electrodes, often made from that conductive boron-doped diamond, can be implanted to safely and stably interface with delicate nerve tissue over long periods. They're being explored for use in fundamental brain research just to help us better understand how neural circuits function. But perhaps more excitingly, they hold potential for clinical applications like receiving complex patterns of brain impulses.
Reading thought.
Well, reading the neural signals associated with intended movements or speech, perhaps, and then wirelessly transmitting those signals to external computers. With sophisticated software decoding those signals, this could eventually enable people with paralysis to control prosthetic limbs, wheelchairs, or communication devices just by thinking about it. Other biomedical uses are emerging too. Researchers are applying thin, ultra-smooth, diamond-like carbon, DLC, or nanocrystalline diamond coatings to medical devices like artificial heart valves or orthopedic implants like hip or knee joints. The idea here is to improve their durability, reduce friction between moving parts, and enhance their overall compatibility with the body, potentially leading to longer-lasting implants.
And I think I read something about diamond surfaces being used as antibacterial agents. How does that work?
Yeah, this is a really clever application that leverages physical structure rather than chemicals. With the growing global problem of antibiotic resistance, researchers are looking for alternative ways to kill bacteria. One approach draws inspiration from nature. Some insect wings, like cicada wings, have surfaces covered in nanoscale spikes that physically rupture bacteria that land on them.
Ouch.
Exactly. So scientists are mimicking this by creating nanostructured diamond surfaces. They can do this using plasma etching techniques on diamond films or by coating surfaces with nanocrystalline diamond in a way that forms dense arrays of tiny, extremely sharp spikes. These surfaces, sometimes called black diamond because they absorb a lot of light and look dark, can literally puncture the cell walls of bacteria that come into contact, killing them mechanically.
And bacteria can't develop resistance to being physically torn apart.
That's the key advantage. It's a purely physical mechanism, not a chemical one that bacteria can evolve resistance to. Plus, these diamond-based nanospike surfaces are often much more durable and less fragile than similar structures made from other materials like black silicon. This makes them potentially more suitable for coating medical devices, implants, or even high-touch surfaces in hospitals to reduce infections. Sometimes they also fluorinate these surfaces, make them super hydrophobic like a lotus leaf, which adds another layer of defense by preventing bacteria from easily attaching and forming biofilms in the first place.
Fascinating. Diamond also seems to have some interesting applications related to the environment, helping clean things up.
Yes, particularly in areas like water purification and environmental sensing. And again, this often involves using boron-doped diamond BDD electrodes because they are so robust and electrochemically stable.
How are they used for water purification?
One promising technique is called electrolytic destruction or electrochemical oxidation. Basically, you use BDD electrodes to pass a high electrical current through contaminated water. This process generates highly reactive species like hydroxyl radicals right at the electrode surface. These radicals are extremely powerful oxidizing agents and can break down persistent organic pollutants, things like pesticides, pharmaceuticals, industrial chemicals that are hard to remove by other methods into less harmful substances, ideally converting them eventually just to carbon dioxide and water.
And why are BDD electrodes good for this?
Because they are incredibly resistant to corrosion and fouling compared to many traditional electrode materials, they can operate efficiently at higher current densities and for much longer times before needing cleaning or replacement. This makes the whole purification process potentially more efficient and cost-effective, especially for tackling really stubborn pollutants. BDD electrodes are also excellent for electrochemical sensing. Their stability and wide electrochemical potential window, meaning they don't interfere with the reactions you're trying to measure over a broad voltage range, allows them to accurately detect very low concentrations of toxic compounds or heavy metal ions like arsenic or lead in water samples. They're also used for analyzing complex organic compounds like endocrine disruptors or pharmaceutical residues in environmental monitoring. And in renewable energy research, BDD electrodes are being explored for processes like photoelectrochemical water splitting, sometimes called photo-EWS.
Splitting water with sunlight to make hydrogen fuel.
That's the goal, yes. Producing clean hydrogen fuel using just sunlight and water. In these systems, BDD electrodes can play a couple of roles. They can serve as stable, electrically conductive support layers for other light-absorbing photocatalytic materials, like titanium dioxide nanoparticles. Or sometimes the BDD itself, perhaps coated with specific light-absorbing nanoparticles like copper oxide, can function directly as the photoelectrode that drives the water-splitting reaction when illuminated. The BDD layer provides a robust, conductive platform and, importantly, can even protect other underlying light-absorbing materials, like silicon, from degrading in the often corrosive electrolytes used in these water-splitting cells.
It really is remarkable how these fundamental properties, hardness, thermal conductivity, electrical behavior, inertness, translate into such an incredibly diverse range of practical applications.
The versatility is truly impressive, isn't it? And beyond the major areas we've discussed in detail, diamond just keeps showing up in numerous other, sometimes unexpected places.
Like where else?
Well, in high-end audio systems, the extreme stiffness and low density of diamond make it an excellent material for constructing speaker domes or tweeters. Because it's so stiff and light, it can vibrate very rapidly and precisely without flexing or distorting, which allows it to reproduce high-frequency sounds with exceptional clarity and accuracy. In fine mechanics, particularly in luxury mechanical watches, thin diamond coatings are sometimes applied to critical wear surfaces like bearings or pivots in the movement. This significantly reduces friction and wear, contributing to the long-term accuracy and durability of the watch. There are also potential applications being actively researched in really demanding environments like the nuclear industry, maybe for radiation detectors or components that need to withstand high radiation fluxes, and in aerospace, where diamond's combination of lightweight, strength, thermal stability, and radiation hardness could be valuable for certain satellite or spacecraft components. Even in the incredibly challenging field of fusion energy research.
Fusion reactors, like tokamaks.
Exactly. Diamond is being seriously considered, alongside other materials like tungsten, for use as coatings on the plasma-facing walls inside fusion reactors. These walls are exposed to unbelievably harsh conditions, extreme heat, intense particle bombardment, high neutron radiation. Diamond's low atomic number, Z6, is an advantage because if any wall material erodes and gets into the fusion plasma, lighter elements cause less energy loss than heavy elements like tungsten. Researchers are still investigating how diamond interacts with the hydrogen isotopes, deuterium and tritium, used as fuel, particularly regarding erosion and fuel retention. But high-purity diamond is already needed for making robust windows for the high-power microwave sources called gyrotrons that are used to heat the plasma in many fusion reactor designs.
And then, of course, separate from all this high technology, there are the applications that really push the boundaries of novelty or luxury, going beyond just traditional jewelry.
Oh, absolutely. You see things like diamond-infused perfumes claiming the diamond dust adds radiance or longevity, though the science on that might be debatable. You find cosmetic products incorporating diamond powder, supposedly for exfoliation, or creating a soft-focus, light-reflecting effect on the skin. People get tiny diamond tooth gems bonded onto their teeth for decoration. Designers incorporate small diamonds or diamond coatings onto clothing or accessories, and you even see temporary body art using fine diamond dust for extra sparkle. These applications might not be leveraging diamond's extreme physical properties in the same way as a cutting tool or a transistor, but they definitely showcase the enduring cultural allure, the perceived value, and the sheer marketing power associated with the idea of diamond, leading to its use in all sorts of creative, sometimes surprising, luxury and novelty items.
Okay, so to try and bring this really deep dive full circle now, we've journeyed from the, violent, high-pressure birth of diamond deep within the Earth's mantle billions of years ago and explored how scientists and engineers have painstakingly learned to replicate and in some ways even surpass nature's process in controlled laboratory environments, achieving incredible levels of precision and purity.
Right, through HPHT and especially CVD.
Exactly. We've delved into its truly unparalleled fundamental properties, that extreme hardness, the incredible thermal conductivity, its unique electrical nature shifting from insulator to semiconductor, its chemical inertness, its biocompatibility, properties that really set it apart from almost any other material.
A unique combination.
Absolutely. And we've seen how, despite some historical challenges and false starts in actually integrating it effectively into technology, many of those hurdles are now being overcome. This is largely fueled by those very advancements in synthesis that allow us to make high-quality, large-area diamond reliably.
The material availability is key now.
It seems so. And this is leading to a real resurgence, a second look at diamond as a critical enabling material. It seems poised to play a vital role in this surprisingly broad and expanding array of modern and future applications, from the very tips of the tools that shape our physical world and the lenses in advanced optics,
to the core components in next-generation high-efficiency power electronics, the potential building blocks of room-temperature quantum computers, sophisticated materials for advanced medical implants designed to safely interact with our own bodies, and even tools for helping to clean up our environment.
It seems abundantly clear, then, that diamond is really no longer just a timeless symbol of love or wealth or permanence that sits locked away in a jewelry box. It is fundamentally material with unmatched properties that is actively enabling technologies pushing the very boundaries of what's possible across so many fields in computing, in healthcare, in energy generation and use, in advanced manufacturing and beyond.
And it's interesting to note that the rise of high-quality laboratory-grown diamond, while certainly disrupting and reshaping the traditional jewelry market and how people perceive diamonds there,
Yeah, causing quite a stir.
it's simultaneously acting as a critical enabler for all this technological innovation. It provides researchers and engineers with more accessible, more consistent, and often ultra-pure material that can be specifically engineered, sometimes even defect engineered, like with those NV centers, precisely for these demanding high-tech applications where natural diamonds just wouldn't be suitable or available in the right form or quantity.
So maybe we should end by reflecting on that fascinating duality of diamond again. Here we have this substance, revered for centuries, for its static beauty, its perceived unchanging nature, its permanence.
The forever aspect.
Exactly. Yet at the same time, it's a material that is constantly evolving in our hands. It's being engineered at the atomic level, manipulated and applied in entirely new ways that fundamentally challenge our very definition of what this incredible substance can actually do. As researchers continue to unlock its secrets and refine its applications, could it be that the most valuable carats of the future won't be measured by their traditional clarity, cut, or color?
But by something else entirely.
Yeah, perhaps by properties like their electrical conductivity or their quantum coherence, time for qubits, or maybe their long-term biocompatibility when functioning as part of a neural implant inside a human brain. It really is a material that reminds us that sometimes the most ancient and seemingly simple things can hold the key to the most advanced and revolutionary futures.
A truly compelling transformation for sure. It's going to be exciting to watch where it goes next.
Absolutely. Well, that brings us to the end of this deep dive. Thanks for listening to All in All.